Hello guys, let's get started. And it's my fault now. I thought that was going to start at 3:30, so I was waiting, and it's totally my fault. And I apologize to the presenters, and I'm gonna do my best here. So without any more delay, just everybody show which room you are. You are in. Let's see if I know if I'm in the right place. Red Bud, and this session is WaSH and Interventions and Services. And our first presenter will be Hannah Wharton and Daniel King, please.
All right. Hi, everyone. My name is Hannah Wharton, and I'm a PhD student at UC Berkeley in the Pickering Lab. And I'm presenting today with Dr. Daniel Kim, who's a postdoc. And we'll be discussing our project on the impact of community-level drinking water treatment on bacterial strain sharing in rural and urban Kenya. There we go. So enteric infections are one of the leading causes of global morbidity and mortality in children under 5, especially in low and middle income settings. And enteric pathogen transmission, as many of you know, through environmental pathways can be described using the F diagram. And so for our study, we focused on enteric pathogen transmission through the fluids pathway. And so enteric infections arise in part from exposure to fecal contamination, due to inadequate access to water, sanitation, and hygiene. So past studies have found that household level drinking water treatment has mixed effects on enteric pathogens. However, community-wide water treatment interventions have found to have the potential to disrupt enteric bacteria transmission. And our project examines strain level transmission. So historically, this has been studied by culturing single isolates, but this ignores strain diversity in hosts, and it misses bacterial species that can be difficult to culture. So we believe that better understanding of bacterial transmission among children in low and middle income communities would inform treatment interventions for rural and urban settings, especially at the household level or the community level. And so our objectives for this study were to identify patterns of bacterial strain sharing among Kenyan children living in urban and rural settings, as well as to determine whether community-level drinking water chlorination disrupts bacterial strain sharing between urban and rural households. So the samples we used for this study were from 2 different studies. The first was the WaSH benefit study, which I'm sure a lot of you are familiar with. It was a cluster randomized controlled trial, and it included a control arm that had unchlorinated water and a water intervention arm that included chlorine dispensers at community taps and household level chlorination. And we randomly selected 120 rural Kenyan households from this study. And this included a target child that was 19 to 30 months and an older sibling. And we used stool samples from this study. And the second study was the Nairobi study, which was a cross-sectional surveillance project. It took place in urban Kenya, and we used all 106 households from this study. It included sibling and mother stool samples, and it was in villages in Dagoretti and Kibera, and Dagoretti had unchlorinated piped water, and Kibera had chlorinated piped water. And so in terms of our methodology, we performed DNA extraction and Illumina sequencing on our stool samples. We then used Strange, which was a tool developed by the Broad Institute, and it is composed of 2 modules, Strangest and Stranger. And Strangest aligns the reads with reference genomes, and then it outputs a list of strains per sample of each bacterial species that we were targeting. And then Stranger compares SNPs and gaps in coverage. And from this, we used a random forest approach that calls strains using statistical outputs from Stranger. And this machine learning model was trained using longitudinal microbiome data sets. And then from this, we were able to get our shared strains between samples. And so in terms of our target organisms, we prioritize pathogenic species as targets for strain sharing. We initially performed strain level identification for species in the escape pathogens. So this includes Enterococcus, Staphylococcus, Klebsiella, Acinetobacter, Pseudomonas, and Enterobacter. We also included species Escherichia, Campylobacter, and Salmonella. And we detected no strains from Salmonella, Pseudomonas, Staphylococcus, or Acinetobacter species. We also included some commensal organisms as well, including Bacteroides and Bifidobacterium. And with commensal targets being strict anaerobes and pathogenic targets or non-commensals being oxygen tolerant or facultative anaerobes, we assumed here that it would be likely that the commensals would not spread as easily through environmental reservoirs, whereas the non-commensal targets that are more oxygen tolerant would spread as more easily. And so now Daniel's going to go through some of our results.
So after identifying sample pairs sharing identical strains, we calculated strain sharing rates within and between households, and we found some evidences suggesting that community-wide chlorinated water disrupted strain sharing. The figure here shows the within household strain sharing rates in the Narabi study, and we found a significantly lower strain sharing rates for all genera and especially commensals in the village supplied with chlorinated water. But we did not see the significant differences for the non-commensal strains. And for the strain sharing rates between households, we observed the similar patterns with the within household strain sharing rates, with a significantly lower strain sharing rates of commensals in a village supplied with chlorinated water, but not for the non-commensal, suggesting that community-wide chlorinated water disrupted commensal strain sharing, but not for the non-commensal strain sharing in these regions. In the WaSH study, we did not see any significant differences for the within household strain sharing rates. But for the between household strain sharing rates, while we didn't observe the significant differences for the commensals, we observed the significantly lower strain sharing rates for the non-commensals, which was the opposite of the Narabi study. Although the effect of chlorinated water varied between these studies, we could still observe the potential that community-wide chlorinated water disrupted strain sharing. So now we wanted to understand how these individuals are connected through strain sharing between households. So in these two strain sharing networks, each of the circle indicate each of the individuals, and the connections between circles indicate that there was a strain sharing events. And the size of the circle is proportional to the number of connections each individual has. And we had, the color of the circle is color coded by the age groups. We had 4 age groups in the Narabi study, which were infants, child, older child, and adult. And in WaSH study, we had 2 age groups, which were child and older child. And one thing we noticed is here, but before I jump onto that, the circles here are positioned more closer together if they tend to share more strains to each other. And one thing we notice here is that among the youngest child group in both 2 studies, we found that they tend to cluster together, sharing more strains to each other. The heat map here clearly shows that the youngest child group in these 2 studies tend to share more strains frequently among them. And this was quite surprising because we were kind of expecting to see lower strain sharing rates for this youngest child group because they would stay mostly at home. But our hypothesis for this is that we're thinking that there is a base level fecal exposure, even though this child stay mostly at home. And because they lack gut colonization resistance because they're at the early stage of gut microbiome, we think they will be more vulnerable to this strain acquisition. Now we wanted to see how water treatment affects this strain sharing of either commensals or non-commensals across these age groups. The left panel here shows the village with chlorinated water, and the right panel shows the village without chlorinated water. And this is the data in the Narabi study. And although, while we don't see any like outstanding differences for the specific age group in terms of like the strain sharing rates, we could observe overall, in general, lower commensal strain sharing rates across all age group pairs, suggesting that chlorinated water was effective in disrupting strain sharing for these commensals for all age groups across all age group pairs. And for the WaSH study, we could observe that strain sharing rates for the non-commensals in the households without chlorinated water was highly enriched between the youngest children. And this could be effectively disrupted by the community-wide drinking water in these regions. So for the conclusions, we found that community water treatment effectively disrupted either commensals or non-commensals consistently in both urban and rural study sites. And we found that children were more vulnerable to this strain acquisition possibly due to their lack of gut colonization resistance. And lastly, in the rural study sites, which was a WaSH study, was especially clustered randomized control trial study. And in this study, we found that chlorinated water effectively disrupted non-commensal strain sharing, especially for the aforementioned vulnerable youngest child group. So we want to thank you for our collaborator, Broad Institute and Kennan Medical Research Institute. And we also want to thank NIH for funding this research. And thank you for the listening. And any questions? Yes.
How is strain sharing in this setting compared with studies that have been done in developed countries with high quality water?
Sorry, could you repeat the question again? First thing I want to say here is that so in this study, we used the metagenome data sets because previously, even though in high income countries, investigating how strains are shared was based on isolating a single species from each sample, and they focused on only like one isolate for a specific genus from each person. But here we are using metagenome data, which we can target like multiple strains across multiple genera at the same time. And that's how I think it adds more to the quality of investigating how strains are shared in these regions. Yes.
For the non-microbiologists among us, what's the mechanism by which chlorination would disrupt strain sharing? So basically, we're talking about would be through sort of sharing of a water glass. What are the other mechanisms?
That is a good question. I think there can be like multiple routes for the like strain sharing. And I think so because people are using like getting their water source from the community water tap, and if it gets contaminated, I think that can be one of the like major routes how like strains disseminate in the community. But I think there can be also like other pathways we're unaware of, like suggesting, I mean, for example, like there can be like fecal exposures happening more frequently in rural area other than, you know, water related thing. And in that case, I think the source in this community can somehow transfer to other communities by like people moving towards, like traveling toward between like two different communities. So it's hard to answer like which is major pathways, but I think water can be one of the major pathways for that.
About the same way we just think of transmission. I mean, strain sharing and transmission kind of synonymous in this context?
Yes, but I think it can be kind of different by like commensals or non-commensals in terms of like how they, in terms of their strain sharing mechanisms. Yeah. Last question. I think we're good.
Yeah, you as I raised my hand, you
Yeah.
I guess if I can have a question, then it would be, when will this be published? It's very exciting, and I'm looking forward to citing your work.
Now we are collecting all the data. We have to start drafting the manuscript. Yeah. Thank you.
You know which one is yours here?
It's already.
Okay. Okay. So our next presenter is Megan Lindmark from Cova. Megan.
Thank you, guys. It's great to be here today. As mentioned, my name is Megan Lindmark. I'm with an organization named Cova. And you may previously have seen presentations from us under the name EOS. We've been through a rebrand in the last year that I wanted to quickly call out. Our new name, Cova, takes inspiration from the covalent bonds between hydrogen and oxygen and water, which I hope appeals to many of you in this room. So a little bit of background that I probably don't need to acknowledge, but a recent study found that our previous estimates of the number of people without access to safely managed drinking water were considerably too low, right? So we're looking at 4.4 billion people without access to safely managed drinking water. And specifically, I want to call attention to the proportion of this number that is driven by fecal contamination. They find that in that most recent study that half of that 4.4 billion is driven by fecal contamination in drinking water. And we have tools to eliminate fecal contamination in drinking water. And so one of those tools that I'm going to focus on today is inline chlorination. And so inline chlorinators are a series of technologies that can be implemented to elevate existing supplies to safely managed at various points within a distribution system. And specifically, these technologies are low cost, they do not require electricity, and they help eliminate the end user burden that comes with household water chlorination or household water treatment. One specific chlorinator that I'm going to focus on is Cova's Chloridora deck. This system is a very simple PVCT, and source water flows in. This is usually installed at a tank that then feeds an entire pipe distribution network. So this would be installed at the inlet of the tank. Source water flows in and then can be controlled to either flow through a tablet chamber where a series of calcium hypochlorite tablets are stacked up, or it can flow through the bypass to then rejoin in the tank to ultimately achieve the ideal chlorinated dose of water that then flows into the distribution network. So this is designed for gravity-fed systems with kind of that ideal flow rate, but this can be adapted to a variety of different systems, and again, does not require electricity. So Cova implements these chlorinators as a part of our larger circuit rider model. Currently, we serve 2,000 plus communities across El Salvador, Honduras, and Nicaragua. And this circuit rider model is a form of supported community-based management. So in these rural communities across these countries, there are water boards that are a group of elected, legally represented, recognized entities. There are usually 8 to 10 water board members that are elected, and they are responsible for the actual day-to-day operation and maintenance of these water distribution systems. And so our circuit rider model provides support to those community water boards. Our circuit riders are technicians who visit about 50 of these communities each month to provide a series of services. And part of that, as I pointed out, is chlorinator installation, but it's also a much larger process in which community water boards receive capacity building around operating these chlorinators, around protecting the water source that feeds these distribution networks, as well as things like water quality, things like actually replacing the chlorine tablets in the chlorinator, et cetera, all of the things required to operate and maintain these systems. In addition to this, Cova supports our model through chlorine distribution and sales. So there are chlorine tablets that I showed you in that last slide that have to be replaced routinely in these chlorinators. And Cova supports our work by selling these chlorine tablets. Our circuit riders also provide routine chlorine monitoring, technical assistance, as well as laboratory analysis. So that's really the bulk of what our circuit riders are doing on a day-to-day basis. They're visiting these communities, they're taking chlorine samples to determine whether or not the chlorinators are operating as expected. And then they're providing kind of a feedback loop. If there is not chlorine in the water, they do a root cause analysis, they provide additional assistance and provide follow-up support as any other problems arise. As you can imagine, if they're visiting these 2,000 communities on a monthly basis, we're generating an awful lot of data. And all of this data is going into our mWater database. And specifically today, I'm going to focus on data collected between 2013 and 2021, around 9 years worth of data that has resulted in over 12,000 chlorine monitoring data points and 18,000 visits in general. And as I mentioned, each time these circuit riders are visiting, they're recording the chlorination levels, they're recording with the type of visit and all of the associated problems and details. So this data set that I'm going to be talking to you today refers to 359 communities, specifically in Honduras, and 12,000 plus samples. And those samples are distributed across the distribution system. So some of them are collected at the tank, some of them are collected at various points within the distribution system. So the objectives are to take this data and actually make it actionable, do something useful with all of this data. And so specifically today, I'm going to talk to you about one objective being that we want to assess the effectiveness of our model broadly, as well as determine kind of the circuit rider model specific drivers of effective chlorination. So how effective is this chlorination work? And what are the things driving either the effectiveness or lack thereof? And the work that I'm talking to today can be found in a publication from last year. So if you want to see more than I'm sharing today, I would refer you there. So first big picture result from all of this data is that 77% of samples collected, regardless of the point and distribution system, had adequate levels of free chlorine residual. So that's above this 0.2 milligram per liter line. This box and whisker plot steps you through the distribution network, like that last figure I shown you. And so you can see that the free chlorine residual is at its highest in the tank, which makes sense. That's where we're dosing chlorine, and then you would expect to see decay throughout the distribution system. But what's important to know here is that across all of these household level points, we're still seeing on average chlorine levels that are above this free chlorine residual 0.2 milligrams per liter, which is a very promising result. This indicates an effectiveness of chlorination, or an effectiveness of these chlorinators in providing chlorinated water, I should say. 77% is by no means 100%. And so we want to know why that is. So each time a monitoring sample is taken and there's not chlorine, our circuit riders are recording the reason that there is not chlorine. And so we've categorized them here, and this is a lot to visualize. So I'll step you through kind of the two different major categories, which are technical errors and human errors. So remember I mentioned that water board that's responsible for the day-to-day placement of the chlorine tablets. That's all of these kind of blue shaded types of errors. So the first would be habitual error. This is a water board that's routinely failing to place the chlorine tablet on a regular basis, versus kind of this occasional error, meaning that this is a water board that this appears to be a one-off incident based on our circuit rider's experience. And then the final one is the failure to purchase chlorine. So they either forgot or could not afford to purchase chlorine in that time period. And that's the lightest shade of blue here. So then the other important, so step ahead there. The other important category is technical failures. So this orange bar is actually failures or lapses due to the chlorinator itself, meaning incorrect dosing by the actual device. Versus this red bar, which you can see is kind of increasing through time, is there's no water present. So this isn't an absence of chlorine so much as an inability to take a chlorine test due to not enough water present in the system. So a couple of worthwhile points is that, you can see kind of through this time period, chlorinator-related failures kind of decreasing. Through the same time period, you can see human error stays relatively routine. That is a consistent issue and a challenge in this work. And then the second that I'll point out is the increase in this red proportion over time. So we're seeing increased water variability across these systems, which would suggest some climate variability induced seasonality to some of the water sampling. So that takes us through the kind of waterboard side of the management system and the results. But what about from the circuit rider side? What about all of those different types of visits? How do those relate to the outcome water quality? So we completed a Spearman correlation analysis between all of the different types of visits that circuit riders can complete and the outcome average free chlorine residual levels. So what's important to note here is that blue boxes indicate positive correlation and red indicate negative correlation. And so this bottom row is the average free chlorine residual level for a given community, whereas these top rows are then the types of visits that are completed and the proportion that they represent of all visits completed. So what I'll call out, because this is, you don't have to interpret all of this, but what's important is that purely the number of visits is the most significantly correlated with this average free chlorine residual, which suggests that purely on visiting repeatedly alone, you see increased, improved access to chlorinated drinking water in these communities. Simultaneously to that, a kind of unexpected result is the percentage of monitoring visits completed. So that's the percentage of monitoring completed across all different other types of visits is negatively correlated with this other visit type. Now, this actually does make sense the more you think about it, because there's a trade-off, right? These monitoring visits are completed monthly, technical assistance on demand. So we could imagine then, given that we know technical assistance visits are well correlated with outcome chlorine, that we might want to see improved levels of technical assistance visits being completed. So some key takeaways in summary. Cova circuit rider model supporting community water boards delivers 77% adequate levels of free chlorine across all samples, regardless of where they are taken in the distribution system. Lapses in chlorination, these are primarily driven by both human error, but also climate-induced variability. And finally, circuit rider visits are very important to chlorine outcomes, but the different types of visits can have different resulting impacts. And so we need to find a way to prioritize technical assistance visits to the communities that need them. Some follow-up research questions that come out of that, how do we better incentivize communities to chlorinate, right? We have water boards who are not reaching that 100% chlorination rate. How do we incentivize them to do so? How does chlorine taste acceptance impact this model? Didn't really talk about that here, but that can really impact whether or not a water board might choose to chlorinate or not. And then finally, I talked about this last question. How do we prioritize the circuit rider's time to be providing the types of assistance that actually drive change? I want to quickly acknowledge our Honduras team, as well as this research was completed while I was at the University of Iowa. And I will take any questions you might have. Okay, I've got several in this row. I don't know which of you would like to go first. Tanner, all right.
More traditional professionalized service delivery where it's their staff who don't do stuff. Is there anything in your research that you would point to, the recommendations or areas of caution that extend to that?
Yeah, I think the key piece that I would point out is that the frequency of touch points with a community can improve chlorine outcomes. Naturally, if in your case, you would have an operator who's actually responsible for that chlorinator, that might not be as critical, but could still be critical in terms of the acceptability of chlorination. So actually providing that additional kind of capacity building to the community, even if there's not a local operator, around why chlorination as a solution makes sense, could, prevent any kind of negative outcomes like community members rejecting chlorinated water, even if it's being chlorinated by your operator. Yeah. Yes, I saw your hand in the back first.
Bad channel. Oh, sorry. I was asking about chlorination in Honduras, specifically of just the concern of the taste of the water. How have you overcome those challenges with chlorination?
Yeah, so two things. One, as I kind of alluded to at the end, this is an active area of study for us, and this is something we want to understand better. In Honduras, we've benefited from the fact that maybe about 20 years ago, there was a lot of investment from the government to try to do chlorination at scale. A lot of those chlorinators were much more complicated to use and ultimately are no longer in use when we enter these communities, but there is an existing, many communities have had chlorinated water at some point, or people have tasted chlorinated water. And the other aspect that I'll add is that we also do a baseline water quality assessment to show the community that their water is contaminated with E. coli, to then kind of validate the reasoning for chlorination from there. Oh, okay, one more, yes.
My question is more regarding the. Thanks. My question is regarding the financial sustainability of the circuit riders.
Sure.
Now, how's that? Are they subsidized, or are they currently able to generate enough income from the communities and water boards? I work a lot in Central America around this, so I'm just very curious. Thanks.
Yeah, so we have kind of a balanced approach where about 50% of the cost of one of these circuit riders and their day-to-day tasks is covered by chlorine sales as well as chlorinator sales. And then the remainder is traditionally from like a philanthropic source. We've also worked though closely with Uptime, and I would encourage you to chat with them if you haven't. Otherwise, to get result-based funding, which then can help us cover a lot of that gap. Yes, are we out of time? Can I answer Mark's question? Okay, all right.
Yeah, so
This one.
here, yeah.
Yeah,
So you say there's more cases of no water present
yes.
and that it's climate related, but couldn't it be, I mean, you try to account for, something wrong with the chlorinator, but couldn't there be like a pipe crack or clogged with sediment or something like that, or more water being drawn, so there's not enough water available? I mean, there could be many reasons for that, right?
Yes, definitely. Yes, that is, I would say the climate variability is probably a generalization. However, most of these systems are gravity fed. So supply is, if there is water flowing from the source, it's generally reaching somewhere in the system. The other aspect is if our circuit rider is not finding water when they go to test at a household, they will go kind of do like a root cause determination. So that includes a visit to the tank. So if there's no water flowing to the tank, the presumption is that's a source water.
Okay, and can you flip to the next slide?
Yeah.
So the monitoring, what does monitoring consist of?
So that's a visit to actually test the level of chlorine, and it usually includes a surprise check to a household somewhere in the distribution network. So they perform a quick free chlorine residual check.
Okay. And technical assistance is in response to a call, right?
Yeah, it's in response to a call or a programmed response to a problem assessed during one of those monitoring visits.
So couldn't it be that when they show up for monitoring, sometimes they get questions that don't get coded as technical assistance, so they don't get the call?
I would say sometimes, but when they code a visit in our surveys, they can code it as monitoring and technical assistance. So generally speaking, they try to cover that. Yeah, good question though. Yeah.
Thank you all. Now, straight to the next presenter, which is Kelsey Pieper from Northwestern University.
Northeastern.
Professor. Which one is you?
This very colorful one.
Okay.
All right. There we go. All right. So hi, I'm Kelsey. I'm going to be talking about disasters and how they change our understanding of perception and how it relates to consumption behaviors. So just to orient us, because I don't know how many people are familiar with wells in the US. So these are distribution systems on people's property. They are not regulated by the EPA, so they're pretty well known to have a lot of contamination issues. So things only get worse when we have flooding events because floodwaters rise. Water can go directly down the top of the casing because they're not fully sealed. They can go down the outside if they're not maintained or constructed correctly. And then they can also get contaminated because of the geology if there's a high surface groundwater potential. And then, of course, you also have, if you're hydraulically connected to your neighbor, you can get contaminated. So basically, flooding events are really bad. And then you add in the fact that flooding events can cause damage both to the on-site water and wastewater. So now we've got fecal matter in the wastewater. So needless to say, a lot of research is coming out showing that after flooding events, private wells are contaminated. Generally looking, we see about 4 times baseline conditions when we do general surveys. When you dig deeper and actually start delineating the data and looking at systems that were flooded versus not, contamination rates are actually up to 8 times, even 10 times higher. So basically, this is really saying that during flooding events, we really need to be thinking about drinking water. Problem is, because these systems are not regulated, it's really at the discretion of the homeowner to do something about it. And we see a lot of problems under routine conditions. So this was a study we did in Louisiana where basically people they had bad risk perception. They didn't think there was a concern, so they didn't do any well stewardship behaviors. What we see after a flooding event is that shifts. People see, they perceive a problem, they know there is something to do, but they don't actually know where to go, who to talk to. They don't know what are the next steps because they're not water operators. And so this is a really big problem that really hasn't been well discussed because we don't do a lot of work after disasters with this community because it's not regulated. But the big thing is most people say is FEMA's coming in with water, states are coming in with water. So people are switching. They're using good avoidance behaviors and getting off of the water and onto bottled water. But we don't actually have a lot of data on that. It's mostly anecdotal. And so what my team was really interested in doing was kind of asking some very basic questions of, after a hurricane, what are people actually drinking? And are drinking behaviors different when people perceive their water to be safe or unsafe? So just really baseline, because we don't actually know these answers. So this is we ended up using data we already collected. So we published a paper after Hurricane Harvey looking at contamination rates. And we used that data to unpack it further to look at consumption and perception. So this was a study that we did with the Texas Well Owner Network, where we provided free well water testing and surveys to 1,500 residents after Hurricane Harvey over a 9-month period. I'm going to focus in on the first 600 samples that were collected in the first 4 weeks of the flooding event. And so in this sampling that we did, we asked a 4-page survey. So we had a ton of different data. And there was 2 questions that we were really interested in. The first is, what are you doing for drinking water source? Are you drinking unfiltered or untreated well water, filtered or treated well water, or have you switched to a different source like bottled water? And then how do you perceive the safety of your water? Do you think it's safe to cook, drink, or bathe in on a Likert scale? So we were really fortunate. Of our 630 residents, 549 actually answered both these questions for us and were supplied by a private well. So we had a lot of data that we could work with to start answering our basic questions. We ended up coupling this with our E. coli results as well as flooding data. So we asked residents if they had flooded. And for those residents that didn't know they may have evacuated, we used satellite data to understand flooding patterns in the community. We did some basic statistics just because we were really interested in the questions. So we did test proportion chi-square, and then we ended up doing a logistic regression. So getting to the good stuff. What we found was that most residents just continued using their well water. So of the residents that we surveyed, 70% continued drinking their well water. Only 30% were on bottled water when immediately after the storm. When we talk about treated, that light orange bar, we found that about only a third of residents were treating their well water. And when they actually talk about treatment, it was not a microbial related treatment device. It was often a sediment filter or a water softener. So treatment wasn't really going to actually help with the microbial problems associated with a flooding event. So we ended up actually grouping them together because we didn't deem that to be fully treated. I want to zoom in on the use of bottled water because I thought this was really interesting. What we found was there was no difference in when we asked residents what their water source was before or after the storm when they were not using their well water. Basically, they were using bottled water before the storm. They didn't trust their water. They didn't like it, so they were never actually using it. And what we found was that 85% were in that category. So only about 15% of our residents that had told us they were non-consumers actually had switched. Most were just always on bottled water. So again, we're seeing that pattern of people are not switching their water source. When we started getting into perception of water quality, we saw it was pretty well mixed. We saw about almost half our participants say that their water was unsafe for drinking, and about a third felt it was safe. We found it really interesting to start delineating perception by water source, or just to see what was going on. And what we found was that if you look at the S's, those stand for safe, N for neutral, and then U for unsafe. What we found was that everyone who felt their water was safe for consuming, most of them were actually still consuming their water. So we're seeing that perception, those models of perception, if you think your water looks good, tastes good, smells good, you're putting it into your body. We're seeing this hold true after the hurricane. The issue was we had about 25% of our residents that told us that thought it was unsafe, yet they were still drinking it. I'm going to get into a little bit more on that later, but that was just really interesting from this pie chart. So factors influencing consumption. So we did a logistic regression, looked at odds ratios to say what are the factors that are linked to increased consumption. And so the first thing we found was that people that thought their water was safe or they were neutral about their safety compared to not safe, they were 2 to 5 times more likely to drink their water. People that had treatment and they had confidence in their well water stewardship were 2 times more likely to drink their well water. And then we found demographics. Residents that are higher income and white households were more likely to drink their water. So again, this is pretty common to what we expect from a water use behavior from the literature. What was really interesting was we found no impact of Hurricane Harvey on our water use or on whether residents were drinking their water. So moving to perception of well water safety, we found that one of the biggest drivers of whether someone thought their water was safe was their ability to do stewardship. They knew where to go, they knew who to talk to, they knew what the next steps were to recover their system or to maintain their system. We also, again, found demographics. Residents that are higher educated, lived in urban areas or white households were more likely to perceive their water as safe. And then we started to see the impacts of Harvey. When residents took mitigation and recovered their system or their wellhead or system was flooded, they were less likely to perceive it being safe. So what it's telling us is that we see this model that we see in our literature constantly, that if you perceive your water to be safe, you are going to be more likely to drink it. We see that your perception of your water was dictated based on the disaster. What we didn't find, what was really interesting, was that if you had disasters and your system was damaged, broken, it really didn't shift your consumption of your water. And this is really important because of how we think about outreach messaging. If we're talking about, are your systems flooded, rather than are you system flooded and do you think it's unsafe? So it's kind of a way to reimagine our outreach. So then the last piece is that was really fascinating with this work is we started looking at water use behavior patterns. So we compiled consumption, perception, contamination, and flooding. So basically we took all of our data and we bucketed it into flooding or not flooded. We then subcategorized that into if people were drinking or not drinking. Again, we did it based on safe or unsafe, and then whether it was positive or negative for E. coli. And this is just telling us where our population sits. So mosaic plot's really nice just to see the distribution. We can add a chi-square and we can start looking at the associations in our data. So the deep red color means we have more people in that category than we would assume under the test of independence. So we're seeing more observations, there's a positive relationship. So looking at this first box, we found that people who were not flooded were drinking their water, they thought it was safe, and it actually was safe. It didn't test positive for E. coli. So this is the first pattern that we saw, which is, again, consistent with our knowledge. There wasn't a problem. People thought it was safe. It wasn't flooded. This was good. Second one, we found people that were flooded. They weren't drinking it. They thought it was unsafe. And it both was and wasn't positive for E. coli. So again, this is pretty consistent. They thought there was a problem. They avoided it. The third problem is the big problem that we're working on right now is we had a non-trivial portion of our population that thought that was flooded, thought it was unsafe, and yet we're still putting it into their body and drinking it, and it actually was positive for E. coli. And so we saw this statistical pattern in here saying that there's a third pattern that we really need to be aware of, because this is an issue with most likely access to resources and information that they knew there was a problem, but did not know how to mitigate it. So just to kind of close out the two big things that we kind of found from this, one, there is a portion of our population that is drinking water that they do not think is safe after disasters. And there is a really big need to improve our outreach and education to make sure these people are empowered to fix their systems. And then the other is when we start doing our outreach and messaging, we need to not necessarily always just think about the system and flooding and damage, but also think about human interaction and behavior with it, because the way they perceive it is going to influence how they engage with their water. So with that, I will say thank you.
Question? Hold on.
Yeah, thank you. There was a lot of really good data there. I'm curious about like the timeline of the surveys that you asked, because I know you said the bulk of this data was from the first 4 weeks, but I guess I'm curious, like if there was a situation where, the flood water had receded after maybe the first week, and then you pulled people at 4 weeks, if you thought that perception would change, or if you had data on how long people would have to be affected for it, because I could imagine it would be different if there was standing flood water 4 weeks in versus someone saying it's been 3 weeks, my water was safe before, maybe now it still is.
That is a great question, and I do not have the answer to it, but I love it. I will say we did it where the way we staged them, and it was there, we were about 3 to 4 weeks up to, but we were trying to get there right as people were coming home. But again, people come home at different pieces. But yeah, I'm going to totally look at that. Thank you for that suggestion. That was fabulous. Yeah.
Great. Did you all share the results of this, like the TCQ or the Texas Water Development Board, any like Rural Water Association in Texas, or how did this translate to better education for well owners?
So we worked with the Texas Well Owner Network, which is through Texas A&M AgriLife Extension. So they are responsible. Well, they're not responsible. They take ownership of educating the well population, and that's kind of their role. TECQ works with, like, they all work with them. So that was why we partnered with them. One benefit was that they ended up working with the drillers to try to raise casings and stuff to try to mitigate the overtopping of wells. So some stuff has come out of it, yes, but we mainly worked with the agency responsible most with education. Yeah.
How many of the wells had water treatment, filter systems, or anything of that nature? Do you know?
Only 6 of our systems out of the 549 had something that addressed microbial contamination. I want to say it was like 130 or so had like a water softener or a sediment filter, something to do with aesthetics. But in terms of health-based contaminant removal, there was 6.
You really ought to report the wells that aren't up above the surface of the ground at least a foot. And did y'all do that too, or?
No, moving forward, we've started doing that. There are no records on these systems. So we're trying to crowdsource that information when we do surveys now, rather than just asking, like, do you have a drilled well, bored well? We're actually trying to get them to tell us what the well looks like so we can ask more questions like that, because just because the water went this high doesn't actually mean it went in. But, oh, I love that. Yay.
Yeah. So, can you go back to the figure with like the 8 different conditions? So you said there's some treatment going on. Did that affect perception of water safety? Like, do people think, oh, it's filtered, but it's just a sediment filter?
We did not ask that. I also, having done validation in the field, I still think there's a lot of misunderstanding of like what treatment actually is, or like I've been there and people have had things unplugged or had things and said no. So it is very much user collected. They do see like sediment filters are seen as a filtering mechanism. I mean, they do. It's just, it's not doing what they think to that level. There is so much space needed in the treatment side of this, but no, we kind of just grouped them because from a microbial standpoint, none of the treatments really did anything.
Right. Yeah. I was just curious if you'd analyzed on perceived water quality and whether they actually think their treatment is doing something, even though it's not.
Yeah.
Right.
Could.
Because we wouldn't expect it to have an influence on the actual concentrations, but on perception it might. And then up here, so you have, let's see, unsafe, safe, and that's perception, right?
Yeah.
And you've got not drinking or drinking, and you've got flooded, not flooded, and you've got positive or negative for E. coli. So that's 4 by 2, right? Each of them are binary.
Yep.
Okay. So how many samples are left in that, like in the one there with the 3 in it?
20.
20. Okay.
Yeah. And so we ended up reducing this down just because doing like a 9 by 9 and adding some of these other pieces it did not change the outcomes. It just made it a lot more clunky. So it is a small portion. It's 20 homes, but that still came up significant and is also 20 people. And that message was echoed with, it was 25% of our population that fell into the I am drinking something that I don't think is safe. So it's kind of a big theme in ours is that people are scared. They're putting something into their body they don't want to.
The three,
Mhm.
the group of three, were they wealthy people or poor people?
We've been looking at demographics and we haven't found any characteristics yet. We're still kind of doing some models and stuff, but like it was all across the board.
Hi, Kelly. That's great. It's brilliant. Thank you. I was just wondering if you picked up on any either self-reported or actual health impacts from drinking unsafe water. Maybe it was beyond the scope of the study.
No, we did. I almost put a slide in, but we're like still in the infancy of that. Yes, we did ask people, self-reported AGI, acute gastrointestinal illness. We've shifted to just saying, have you had diarrhea? We did find 6% of our population did have self-reported AGI. We didn't find anything with E. coli, but we did find if your system did get flooded, you did have a higher rate. So we're still playing with that. That's still in the works. But yeah, that is, I mean, studies are coming out saying that we're starting to see diarrheal rates increasing after these flooding events. Yeah.
Okay,
All right.
thank you, Kelsey.
Thank
Thank you all the presenters and all of you for being here. So I invite you to the happy hour right now and seeing the posters over there too. Thank you.
No, this is a video. I broke down in Virginia. We did hurricane. Yeah.
Nobody's gonna ask any questions. She said that nobody is gonna ask any questions.
Oh, no. Yeah, I'm excited. That's great. I'll talk to newspapers and stuff like that. Good.
So, would you like to can I borrow the screen for a second?
Yes.
You want to be really excited?
Yeah.
Could I just
Stop
disconnect
sharing.
like the
All right, you do you.
I just need to disconnect this one. We wanna like not record that.
Why I just imparting brilliant bull fun.